So with Newton's laws, we start talking about a different branch in physics, and that's dynamics. Dynamics deals with the forces that cause the motion. So Newton came up with three laws. The first law is also called the law of inertia, which says that an object at rest stays at rest an object in motion stays in motion unless acted upon by an outside force. Alright, this is not very easy to see in everyday life, because if we push an object along a table, we know it will stop, so it will not stay in motion. Well, the reason it's stopping is because there is this outside force, in that particular case it's friction, that stops the object. It is easier to see an object at rest staying at rest, because if we just leave that block there and return 20 days later, it will still be there unless somebody else moved it. So this is the first law, the law of inertia. The second law says that the sum of the forces acting on an object will give that object an acceleration. So there is an equation for this. That's the sum of the forces, and forces are vectors, so we have to put the vector symbol over that. It's equal to the mass of the object times the acceleration it will attain. Now, forces have a generic symbol F, and again it is a vector, so there will be a magnitude and a direction associated with it, are measured in newtons. The symbol for newtons is just capital N. M is the mass of an object. The mass is a quantitative measure of inertia. The SI unit for mass is the kilogram. And then acceleration is something that we've talked about in an earlier lesson, is measured in meters per second squared. So really, if we look at the unit for force, we have the newtons are equal to the unit of mass, which is the kilogram, times the acceleration, which is meter per second squared. So 1 newton is 1 kilogram meter per second squared. All right, the third law says that every action has an equal and opposite reaction. So what this means is that if I push against a wall, the wall is really pushing against me. The way I know that is because I don't go through the wall as I push on the wall. So this equal means equal in magnitude, and opposite reaction means it's going to be in opposite direction. What's more is that the force that I exert on the wall is experienced by the wall, and the force that the wall exerts on my hand is experienced on my hand. So these forces act on the two things that are in contact with one another. So these are Newton's three laws. The law of inertia, saying that an object at rest will stay at rest, an object in motion will stay in motion unless acted upon by an outside force. The second law is the one that actually has an equation associated with it. So the sum of the forces that act on an object gives that object of mass m a certain acceleration, and that acceleration is in the direction of the net force that acts on the object. And the third law says that every action has an equal and opposite reaction. Now, let us look at some of the forces that we encounter in mechanics. So, the first force is the gravitational force. So, the gravitational force has this form. F is G m1 m2 over r squared. G is the universal gravitational constant, and that's 6.67 times 10 to the negative 11, and the units are Newton meters squared divided by kilograms squared. So it looks like this gravitational force is actually really small, since the gravitational constant is 10 to the negative 11th. So let's see what the other things in the equation are. The m1 and m2 are two masses, and r is the distance between them. So what this equation says is that any two massive objects, any two objects that have a mass and are separated by a distance r, will exert an attractive force on one another. So here is object 1, and here is object 2. The distance is the center-to-center distance. So r in our equation is the center-to-center distance. And the reason for that is because when we're dealing with a gravitational force, we really are dealing with really massive objects. So by massive objects, I mean the sun, the earth, moon, things like that. So the radius of the sun, earth, and moon really matter when we're talking about the gravitational force. Now, of course, every single object on Earth is attracted by the Earth with a gravitational pull. So then, when we say that the sum of the forces that act on a certain object M is going to be the gravitational constant times mass of this object M times the mass of the Earth divided by the distance squared. Now, this distance is the distance from the center of the Earth to the object. And since the object on Earth are tiny compared to the radius of the Earth, this r is basically the radius of the Earth. So sum of the forces then by Newton's second law is going to be mass times acceleration. And I didn't put the vector symbol over them because all of these forces act towards the center of the Earth. So when we're solving for the acceleration of gravity, this is what the A in this equation is, the mass of the object cancels out, so we're just left with the gravitational constant, the mass of the Earth, divided by the radius of the Earth squared. And when we plug in those constants, we get something like 9.8 meters per second squared. So this is how we figured out the acceleration of gravity. Now, since on the Earth we don't always have to write out the formal equation for Newton's gravitational force, we have another force that we call weight. The symbol for weight is usually W, and weight is just mass times this acceleration of gravity. So G is 9.8, and it always points towards the center of the Earth. Another force is the normal force. There are various symbols for the normal force. I will use F sub n. And the normal force is a force of contact. So it only comes up when two objects are in contact with one another. So let's say that we have a table and we're placing a block on the table. The forces that act on this block are going to be its weight, and the fact that the block is not going through the table means that something is holding it up, and what is holding it up is this normal force. So I'm trying to draw these forces at the point where they're actually acting. So for the weight, it's acting at the center of mass of the object. For the normal force, it's acting at the surface of the block. So that's why I start my vectors where I do. There's this reason for it. Now, of course, by Newton's third law, every action has an equal and opposite reaction. So that means that the block is pressing down on the table itself. So this will be your reaction force, negative Fn, but this blue force is acting on the table. So whenever we're solving problems with forces, we always pick an object of interest. In our case, this object is the block. All right, another force would be the tension force. Tension force has symbol T, and it is the force in a cable, string, rope. You get the gist. So let's say that we have an object on a table and it's being pulled by a rope. Well, that rope is exerting a tension force on the object. The other forces that act on the object are the previous forces we had before. So we have the weight and we have the normal force. Okay, so now we have three forces acting on this object. And whenever we're trying to solve for some of the forces, Newton's second law, we have to look at the direction these forces act in. So it looks like the normal force and the weight are in the y direction. They're both along the y direction, but the tension force is at some angle. So the tension force is not in either x or y, so we have to break it up into components. So here we have t sub x, and then here we'll have t sub y. So now we have forces in only x and y directions. If I were to draw what we call a free body diagram, where we only draw the object as a dot and then put the forces acting on that dot, then I would have the weight going down, I would have the normal force going up, I would have the y component of the tension going up, and the x component of the tension going to the right. So these are the forces then that act on the object. All right, let's keep looking at different types of forces and then we'll combine them in a bigger problem. So another force would be the friction force. Now, there are two types of friction forces that we encounter. One is static friction, and the other one is kinetic friction. The symbol for the friction force is usually lowercase f, so then static friction gets a subscript s, and the kinetic friction gets a subscript k. Now, a static friction, that is when an object is, for instance, on an inclined plane, but it doesn't slide down. Static friction keeps it in place. Now, if we increase the angle of that inclined plane, then the object will start sliding down, in which case the kinetic friction takes over, and we're dealing only with a kinetic friction. So we cannot have both static and kinetic friction in the same situation along the same axis. So we can't say that an object sliding down the plane has both static and kinetic friction. Now, friction force has an equation. So the kinetic friction is equal to the coefficient of kinetic friction times the normal force. The static friction actually has various different values. So if you place something on a horizontal table, it won't slide. Then if we incline that table, it will still not slide, but the static friction will be different. And at one point, at one particular angle that the table is inclined, the object will start sliding down. So that's when the kinetic friction pops in and the static friction disappears. So this static friction then has a value between 0 and the mu Fn. Okay? So again, we're using the kinetic friction when the object is in motion. We're using the static friction when the object is at rest. Another force would be the elastic force. And there is really no specific notation for the elastic force. It could be F elastic or F spring. There is no unique notation for it. I would probably write it as F elastic. And the equation for the elastic force is actually given by something called Hooke's law. So the elastic force is negative kx. The k is the coefficient, is the spring constant, sorry, which is specific to the size of the spring, whatever material the spring is made of, things like that. And x is a displacement from the equilibrium of the spring. So displacement from equilibrium. The negative sign has to do with the fact that the elastic force is a restoring force. So what that means is that when we're stretching a spring, the spring wants to restore to the original shape. So restoring, it pulls back away from the direction that we're trying to exert the force in to stretch the spring. And the other direction is also true. If we're trying to compress a spring, the spring will want to go back to its uncompressed length, so it will react with a force that is a restoring force pushing against the applied force. Another force that we deal with in mechanics is the buoyant force. And that force usually has the symbol F sub B. For this, we actually need to talk about fluids a little bit. And then a law that governs this buoyant force is Archimedes' principle. But we will discuss this later on when we talk about fluids. There are other forces that we encounter in electricity and magnetism, like the electrostatic force or the magnetic force, but we will talk about those things a little bit later. So in the next example, you will see a combination of these forces that act on an object and will work with Newton's second law to solve for the acceleration of that object.